Welcome back. We're to our discussion of heat pump models in GLHEPRO. I'll got two more parts, or there's two parts to this example. So in the first part, we'll just look at the data and what we're going to do with it for a specific case, and then in part three, we'll do it live in GLHEPRO. Okay, so this is a water-to-air heat pump, and manufacturers such as ClimateMaster give fairly complete maps of the performance as a function of the source side water flow rate, the load side airflow rate, um, and also there are generally corrections, at least with American heat pump manufacturers, for different inlet air conditions and antifreeze. Sometimes there's corrections for other things, um, like different options on the heat pump. So I'm going to try to make this a generic example. In other words, I'm not actually going to pull up the manufacturer's data sheet. Instead, I'm going to show you what I pulled up. And what I pulled up was this is for a 3-ton heat pump, a nominal 3-ton heat pump. Um, and this is the cooling data. Here it's in BTUs per hour and degrees Fahrenheit. It's in degrees Celsius and kilowatts. So TC is the total, well, EFT is the entering fluid temperature. TC is the um, total cooling provided by the unit. And that's total as in sensible plus latent. And of course, you probably realize this as conditions change in the space, the amount of, say, the humidity in the space changes, or the humidity entering the unit. Of course, the actual amount of latent heat transfer will change. The manufacturer has a way of correcting for this, but it doesn't really extend to a model, for example, that we could somehow, certainly not with the approach we're taking, readily account for changing inlet conditions to the unit. The heat pump power here is in kilowatts. If you're from somewhere where they use SI units and you're wondering why we use BTUs per hour, here in kilowatts here, it's because we pay for electricity and by the kilowatt hour. So that's the heat pump power in kilowatts, and then the heat rejection rate to the ground is in this last column. And if you convert the kilowatts here, say, to BTUs per hour, and add the total cooling to the compressor power in BTUs per hour, you will get either this number or something very close to it. So I actually did that, calculated, and everything was within 1/10 of 1,000 BTUs per hour, and presumably that's just rounding errors. Right, and then here I've converted this to SI units. Okay, now I say this is uncorrected. Let's see, I didn't put this on the slide, but this is actually for a specific flow rate, so 6.8 gallons per minute, and the manufacturer gives also data for 4.5 gallons per minute and 9 gallons per minute. It's for a specific airflow rate, which is 1,200 cubic feet per minute, and the manufacturer also gives data for 860 CFM. So those are all tabulated, but the manufacturer also gave this for an entering air condition of 80 degrees Fahrenheit, 67 degrees Fahrenheit wet bulb. In my opinion, since the airs, of course, this depending on how you set up the system, if you're mixing outdoor air in with the return air, yes, you could have this sort of condition. But if you have a separate, say, a dedicated outdoor air system, and this is just the return air, I would say this is probably a bit on the warm side. I don't know. Let's just say most Americans aren't going to run their unit so there's a return temperature of 80 degrees Fahrenheit coming from the space. So I've picked what I consider to be a more reasonable entering air condition, and the manufacturer has a way to correct for that. And so I did that. Also, in this particular system, we're going to use 15% methanol, so it makes a small difference. Okay, and I'm going to gloss over how the corrections done or exactly what the numbers are. You can figure out the net effect if you want by comparing, each value to the comparing each value to the one on the previous slide, you'll see some things they have very little effect, right? So you see just a slight change in the power, but you'll see more change in, say, the amount of cooling provided here. So we use about the same amount of power, but we have a lot less cooling provided, so that has an effect on how much heat rejection we have, for example. So I'm just doing this as sort of just a rough example of what might happen if you try to make it, try to correct the data for something closer to your actual conditions. Okay, likewise for the heating data, this is the uncorrected heating data. Some of the abbreviations are the same, but the HC here is the heating capacity, and the HE is the heat extraction rate, or what we called in the heat pump model earlier, the heat of absorption, how much heat we're absorbing from the ground or how much heat we're extracting from the ground. Okay, now if we correct this, the manufacturer's entering air temperature for heating was 70 Fahrenheit, which I think is probably, just say it's reasonable if it's return air from the space. It's pretty close to what it probably will be. The manufacturer actually gives performance data for below 60 Fahrenheit, gives it for a 15% methanol water mixture. Above 50, at 60 and above, the data is only given for pure water. So there's a way to correct for that. So in the shaded region, I corrected that. So you can, again, you can compare the two if you want. Okay, now we're interested primarily in predicting heat rejection rate and heat extraction rate. So I've plotted that ratio, right? And the blue here is the uncorrected, and the orange is the corrected. And you see there's a slight difference. And by the way, this heat pump has it's quite an extended range. This is extremely high temperatures to provide cooling with. So I would be surprised, at least in this part of the country, if we design the system with design temperatures much above 90 Fahrenheit. So probably we're more in this range, but you can see the the difference between here and here is maybe 3% or so. So you can correct to your heart's content or develop more advanced models to come up with these values. If you simply, in this case, if you simply use the manufacturer's data, you'd probably be off by a few percent in the amount of heat you were rejecting. It's, I'll say it's well within the sort of other errors that we have in the system. Okay, and for heat extraction, right, there was basically no correction in this region. In here, there was little correction. The actual change, and maybe I have a typo here because it seems like there should have been more or less a fixed ratio. Okay, so I went back and just checked that quickly, and sure enough, there was just a slight discrepancy in how I'd done this. Once I'd corrected the data, the manufacturer doesn't give a correction for the heat extraction rate. So if you want to find the corrected heat extraction rate, you actually have to calculate it rather than just use the tabulated values, and that's what was giving a slight difference between the two. So now I calculated them in all cases, and now you can see basically it's pretty difficult for heating because it was only a small change to see the difference. Okay, so we could in Excel develop curve fit equations, but actually GLHEPRO will do that for us. So we'll come back to that then and do it a live demo.